All right, so welcome everyone to this talk called Get the Spidermonkey off your back, so exploiting Firefox through the JavaScript engine. So first off, quick slide for who we are. So basically we're security enthusiasts. We do vulnerability research on our free time as part of a group of friends called Phoenix. We also play CTF quite extensively with teams that Sleep on Repeat and Kid CTF. Memory only for two properties, and the answer kind of intuitively is no to that. So it will basically switch to kind of a hybrid approach to storage, where the array is called a sparse array now, where basically it's still going to leverage the elements pointer to store certain properties and do direct indexing into that. But then for the really high index and the ones that are kind of isolated with not a lot of elements, it's going to use the shape, where it's going to store the index inside the slots and the name, this time the name referring to the index that you set. And that's about it really. That's how the objects are stored internally in a nutshell. So now let's talk just a bit about JavaScript values, right? You know, I mentioned the integer free, the string hello. You can have an object with a property a set to free, for example. How is that represented internally? So Spidermonkey uses something called NAN boxing, and on 64-bit platforms, which is what interests us nowadays mostly, they use the fact that a user space virtual address will only ever use 47 bits on x64. So they have 17 bits that they are free to use for something they call the tag, and that's basically going to contain metadata about the type of value that you have in the 47 bits. So for an integer, you will have a certain tag value, and you will see the value free encoded in the 47 bits. If it's a string, for example, you will have a tag that says this is a string object, and the thing is actually a pointer to the string object in memory. So what that means for us as an attacker is, right now, with our limited knowledge, we don't have a way to actually write whatever we want in memory, right? Because if we set the integer value 3 on an array, it's actually not writing 3 in memory. It's going to write 3, and on the top 17 bits, something that we don't want. And with that, I'm going to let Edgar.
Alright, so after this short introduction, we can now actually look at a bug and how to exploit it. So for this presentation, we've chosen a bug which basically uses two main features, which are web workers and shared array buffers. So web workers are basically just a way to execute your JavaScript code in the background, because usually your JavaScript code runs sequentially. And basically they added this feature that you can start up a worker which will execute the script in the background. And these workers are completely separate from the main script. They don't share the same context. So if you define a variable in the main script, it will not, you cannot access it on the worker. Therefore, they provide a kind of like a communication, there's a communication between the main script and the worker thread via post message. So basically, like you would, you can send to, you can send to, you can send messages to iframes or other tabs. You can do the same with workers via post message. And as I said, the contexts are different. So each worker will have their own copy of an object. But if you want to share some memory between all workers or between two workers, you can use something called shared array buffers, which are basically just array buffers, but the underlying memory is shared between all instances of that shared array buffer. So if you send to a web worker a shared array buffer, the underlying memory will actually not get copied to the worker, but it will be shared between the main script and the worker. So here's a quick example for a web worker. So basically you just do a new worker and you provide a script like worker script JS, and it will fetch the script and execute it in the background. And then you can send a simple message to the worker with a post message. And here you can put almost any kind of object, and it will get transferred to the worker. And then basically the way the worker receives the messages is he registers an on-message listener, gets the message, and then he can do whatever he wants with that object. And it works vice versa too, so the worker can send messages to the main script too. And the way the object here is transferred is it will get first serialized by the structured clone algorithm, and then internally it will be transferred to the worker, where it will get deserialized. Now, the serialization basically, like the structured clone algorithm, basically just creates copies of your objects. So, like this object will actually, the memory for this object will be copied into the worker's context. So, if the worker changes something on this object, it will not be reflected here. But if you look at shared array buffers, they look like this in memory. So they have the four members that we have already seen in the introduction, and they have this shared array raw buffer pointer. And when you send the shared array buffer object via the post message, the structured clone algorithm will actually not clone this shared array raw buffer. So the new instance of the shared array buffer will still point to the same raw buffer, so to the same raw memory. And well, that's all we need to know basically to find the bug. So let's look at some of the code of the shared array raw buffer. So since it's a raw memory that is basically has several references to it, it keeps a ref count here, and the ref count is basically just uint32. And each time you send a shared array buffer, it gets copied. Well, the structured clone algorithm will call add reference, which will increment the ref count. So that way we know when there's no more references onto the memory, and we can free the memory, which basically happens in drop reference. So whenever one of the shared array buffer objects will get freed, the drop reference will get called here. It will decrement the ref count. Then if the ref count is non-zero, it will just return. But if the ref count is 0, means there's no more references to that memory. The memory gets just unmapped. So yeah. So my question is, can somebody spot a bug here in that code, like, because there's a bug right here. For a beer? Nobody? Okay. Well, what you should think about is this increment here happens without any kind of checks. So what would happen if you increment it, let's say, 2 to the power 32 times? The thing that will happen is basically the ref count variable will overflow because it's int 32. So in the beginning, ref count is 1. Then you add an add reference, then it gets 2, 3, 4, and so on. And at the end, it will be like 0xFFFFF. Then you add one more. Then it overflows. It will be 0. And you add one more, and then it will be back 1. So if we call add reference 2 to the power 32 times, the ref count afterwards will be equal to 1. But we actually have a whole bunch of references to the memory. And now if we manage to call drop reference on just one of the shared array raw buffers, it will decrement the ref count. And because the ref count is 1, it will decrement it will be 0. So it will go in here. It will unmap the memory. And well, the memory gets unmapped, and we still hold the references to the memory. So it's basically a use after free at that point. So we can allocate new objects and well, manipulate them. So yeah, well, that's quite a simple bug. So I guess we can just exploit this. But in fact, it's not that easy, because if you think about how we can call add reference, there is only one way to call it, is via this post message, as I've already said. And the way post message works, it will just serialize the buffer via this write shared array buffer. And in this write shared array buffer, there is a add reference, as expected. Then it will go through some black box, it will get transferred to the worker thread, where then it will get unserialized via the read shared array buffer. And if you check the code of the read shared array buffer, you can see down here, well, it will read in the serialized data, and then down here it will in fact allocate a new shared array buffer object. And these two are like always linked together, like in the Firefox browser. You cannot call just this method without this one being called. So every time we call add reference, it will actually also allocate a new shared array buffer object. So, well, this would not be a problem because normally, but the problem is we need to call add reference 2 to the power 32 times. And if you think about the size of shared array buffer object, it's 48 bytes. And if you do the math, you will find out you actually would need 192 gigabytes of memory to actually overflow the ref count. And well, that's just too damn high. So we need more bugs. And luckily for us, there's quite a nice bug. Well, it's not really a bug, but well, yeah, it kind of is a bug. So think again about the structure. So first we call write shared array buffer and then read shared array buffer. But it turns out that if we manage to somehow get an error between the two calls, then this one will have executed while this one will not execute. So our goal is to find basically a way to make this function throw an error before this one can execute. And then this will basically result in a reference count leak, because in that case we would add references to our ref count, even though we have no new actual references to it. So let's look at implementation of the structured clone algorithm. So this is where the objects get serialized. The way it works, it gets a value, and then it just checks the type of the value. So for example, if the value is a string, then it will serialize it as a string. If it's an int, it will serialize it as int, and so on. And if it's an object, then it will further check if it's some type of special object, for example, a shared array buffer. And if it's a shared array buffer, it will call write shared array buffer and add the reference what we have seen before. And but if none of these if statements match, then basically it will throw a data clone error, and that's where we want to end up. Because if it throws this data clone error, it will just stop the execution of the post message, and it will never the new shared array buffer object will never get allocated. And the way to do that basically is structured clone algorithm is recursive. So it means if you have an array of objects, it will first serialize the array, then all the objects after that. So what we can do is we can find first an object that cannot be serialized, which is, for example, a function, and then basically just call post message with an array that has as a first element a shared array buffer, and then as a second element a function. So it will start to serialize the array. It will serialize the sub, so it will go in here. It will call the add reference, so the reference gets the ref count will be 2, and then it will try to serialize the function, but there's no if statement here for the function because it cannot serialize functions, and then it will fail. And then it will also throw an error message, so that's why we wrap it in a try catch so that it doesn't stop our whole script. And so that way we can increment the ref count without actually allocating new objects. And without this reference count leak, the whole the buffer, the integer overflow bug from before would not be exploitable. And so yeah.
Right. So it's spawning time now. Okay, so now we should have what we need to actually write an exploit. So, like, first we'll devise the exploit strategy. So, first off, what we'll do is we actually trigger the use after free. So, as we said, we'll call add reference to the 2 to the power 32 times, and then call drop reference to make sure the memory is freed, where we'll still have reference to it. then with pretty much any use after free situation, we'll reallocate good target objects, and we'll see in a while what a good target object is in that scenario. So that the freed memory is reused, and then we can modify these objects. Then basically we'll see from step 2 how we can achieve an arbitrary read-write primitive, so then we can read and write from wherever we want in memory. Then we'll have to defeat ASLR because of course Firefox, as you would expect, is compiled with, like, everything is compiled with ASLR, so all addresses are randomized. And then final step is to actually gain code execution. Right, so first off, trigger the use after free. So it's pretty simple as with what we've seen before. So we'll just make 2 to the power 32 copies, or also make sure that the ref count is actually overflowed to 1. Then we'll call drop reference. And the way we do that is we just create a bunch of copies. We overflow the ref count, and then basically we'll force the garbage collector to run once. So it's a bit out of scope, but basically this function does that. It actually, like, the garbage collector will run based on certain things happening. That actually triggers a garbage collector run. And the way it works in a nutshell, basically the garbage collector will try to find objects to which it's confident you don't have any references anymore. And if it's confident that you don't have any reference anymore inside your script, it's actually going to free those objects. So we'll basically create a bunch of copies and keep reference to them except for one, and trigger the garbage collector, and that basically will free the memory. So now step 2 and 3 actually, which we need a good target object to reallocate in the freed memory. And for that, basically, we're going to use array buffers. If you remember, right, because of JavaScript values, we can't just use plain arrays because we don't have full control over what's written. But array buffers are a bit different. So array buffers, they have the same layout that we've seen, right, like the first 4 elements, and they actually have a data pointer which points to a region of contiguous memory. And the way you use array buffers is you can declare typed arrays on them, where actually this time, if you declare a uint32, what you write inside the script is actually what will end up in memory. So they are basically a blessing for attackers. Really. And what's important to know as well is that up to a certain size, that data pointer, the memory for it, will actually be allocated right after the object itself, so it will be inlined, basically. And the reason why it's good is because then we can create a bunch of array buffers and set their first element to a certain value, what we call a marker value. And then by looking at them, we can actually, by looking at the memory, if we find the marker value, we know that somewhere before lies the header, then we can pretty much know where the data pointer is in memory and be able to write to it. So how it looks like basically from a high level point of view. So we have the shared array buffer, which points to the raw memory. We overflow the ref count and trigger a free. So now we still have a reference to freed memory. And we're going to allocate a large number of array buffers, large enough so that we're confident the memory is going to be reused at some point. And then we'll mark those array buffers, look for the value, and the array buffers is going to have a pointer to the data as we've seen before, and now we're basically able to modify that value to make it point to wherever we want. And then with that we can read and write from the array buffer, so we can read and write from memory. Cool. So now we basically have an arbitrary read-write primitive, but we still have no addresses, right? So we can read and write from anywhere we want, but we don't know where we want to read and write from. So now what's left for us to do is defeat ASLR, and it's actually not that difficult now that we have an arbitrary read-write primitive. So it's important to, JavaScript functions are actually also represented internally, and as you can imagine, one of their members is actually a function pointer, which points to the location in memory where that function code is residing. And some of the functions in JavaScript are actually implemented natively. So that's the case for the date functions, JSON functions. So these are implemented natively inside the JavaScript engine. So the pointer that you will find inside the object itself is actually a pointer inside the shared object, so libzul, which contains the Spidermonkey code. So just by setting a native function as a property of an object and just basically reading a small chain of pointers, we basically end up with an address inside the shared object. And from that, right, ASLR only randomizes the base address at which the shared object is loaded, so we can just use an offset to know where the object is located in memory. So now basically we have the address of libzul. Then we won't go into too much details, but from that we can leak libc by reading the GOT. We can leak the stack by reading the environment variable from libc. we pretty much can link the base address of anything we want. So the last thing for us to do now is actually get code execution. So we can think about the different ways that we have. So the first one, pretty standard. If you play CTF, that's kind of bread and butter. You corrupt a GOT entry to redirect the control flow of a certain function to system. Basically, system in libc, for those who are not familiar, just executes the string that you pass inside the shell, so you can run shell commands with that. We can use return-oriented programming. Should be doable. We have the address of the stack, but it's always tedious, so if we have something else, let's use that. And third, which is pretty standard when you try to exploit JavaScript engine, is to actually get a JIT code page, which should be, used to be both writable and executable, so you could just put your shellcode there and then call the function that was JITted. But Firefox has a mitigation which they call WXOR-X, which basically means that their JIT code page are actually never both writable and executable. So it seems pretty hard. And for the purpose of this research, right, we just needed to demonstrate that we had code execution. So we went with the first step. The good thing for us is that first step actually requires a bunch of things. So the relocation section needs to not be read-only, which is the case for Firefox actually. And we also need a good target method. So that's the last thing that's left for us to do, right? Like, you know, so the goal now is to call system with a string that we control. And for now, we need to find a method that's called inside the JavaScript engine where the first argument is actually of the same type, a pointer. And basically for that, we use the copy within section function, which is defined on typed arrays. Copy within actually uses memmove. Memmove first argument is actually a pointer to memory. So basically, by using the small snippet of code that you see here, we create a typed array. We basically write the byte of our command we want to execute to that typed array. And then using our arbitrary write primitive, we just replace memmove with the address of system. And by calling copy within, it will actually call system with that string. And Edgar is going to be doing a demonstration of that now.
All right. So, well.
All right. So basically, what Edgar is going to do now is first he's going to show you the exploit a bit.
So yeah, this one is our exploit here. So it's rather long, but just a few things. So here you have the do GC, which triggers the garbage collector. Here we basically do the ref count overflow, and then over here you can see all the allocations of the array buffers, and we mark them with a value to find them afterwards. And well, there's some other stuff going on that we didn't talk about, but anyway, in the end, what we do for this demo, we will just spawn a simple reverse shell to a server, and well, we will see if that works now. So I will just connect to my server now here, and I will run a local server to serve the exploit.
So basically now Edgar has a local server which will serve the exploit. So now he's just going to, so he starts the listener on his server to receive the reverse shell. And
yeah, so here on the left is my server, and the right is my local machine.
And basically now he's going to browse through to the page that has the exploit with Firefox. And hopefully, if the demo goes on our side, we should see a reverse shell arriving.
So yeah, so now it does all the allocations, and you just have to wait a few seconds that it does everything. And then we should get a reverse shell here on the left, hopefully. Yeah, that looks good. So, well, it's somehow fucked, but anyway, I can just start a calculator maybe to show you.
So that's it. Any additional information, you can go to these links. Once again, we'll publish the slides today during the day or this weekend. So, and the full exploit is also on GitHub.
So we got time for one short question. If any, yeah.
Yes, hello. How did you find the bug? Did you use some tools or did you read the code?
No, so these bugs are actually all credits to our fellow members. So Silo is not here today, of course. And no, like the way you find them is manual source code auditing. It's pretty, like, it's really hard to find bugs. Yeah. You can fuzz some parts of the engine, but there are other bugs that you probably can't find with fuzzing. That one seems to be a good candidate, at least to me.
Any other question?
Countermeasure?
Yeah, so as far as countermeasures for a specific exploit, they could compile the thing with the relocation section marked as read-only. The GOT entry corruption would not work. It's also important to note that as far as like patching that specific bug, what they did is simply implement a reference count overflow, and they also set a hard limit on the number of references you can have. Like having 2 to the power 32 references to the same underlying memory seems completely unrealistic. So they basically capped the number.
And they also fixed the second bug with the reference count leak. So now if you actually crash before it crashes the structured clone algorithm, it will actually drop a reference again. So you cannot you cannot exploit it anymore.